In this lecture, we'll go back to looking at a variable coefficient linear system, the acoustics equations, but now in a heterogeneous medium, which means that the material parameters that define the material that the waves are propagating through are varying in space. And we'll start by looking at one space dimension and talk about reflection and transmission at interfaces and how we can do that in terms of Riemann problems, and then look at the extension to two space dimensions as well. So recalling some things from chapter 2 on just one-dimensional elasticity to set the stage, we can write the elastic wave equations in one space dimension in terms of the stress sigma and the strain epsilon, along with a background density and the particle velocity. And that gives the system of equations that's shown at the top here in one space dimension, where we have equations for the strain and the momentum, which are the conserved quantities, and the fluxes are the velocity and the stress, respectively. But we're going to now restrict our attention to a linear problem where we assume deformations are small enough that the stress sigma as a function of the strain epsilon can be defined by Hooke's law, that sigma is just some constant k times epsilon. And k is the bulk modulus of compressibility, similar to the parameter that comes out in the acoustics equations when we look at gas dynamics. And this system of equations, if we now rewrite it in terms of sigma and u, rather than epsilon and rho u, in the linear case we can do that, and we end up with this system of equations, which is a system of two equations with this coefficient matrix A that looks a lot like the coefficient matrix for linearized gas dynamics. It only has a minus sign instead of a plus sign, and that's because this is really equivalent to acoustics, but the sigma, the stress that's defined in the elasticity, has the opposite sign of the pressure that's defined in gas dynamics typically. But it's basically exactly the same equations. So when we linearize elasticity or when we linearize gas dynamics, we get systems of this form. And in the past, we've looked at the system with k and rho being constants. Now we want to look at what happens if the material is heterogeneous and rho and sigma are allowed to vary with x in one space dimension. So then in the elasticity equations, if we write it in terms of the conserved quantities, the strain and the momentum, we get a system of conservation laws in those quantities. And one can solve the variable coefficient equations in that form. But just like with the variable coefficient advection equation, there's another form. If we use a different set of variables, we can write it in a non-conservative form. That's sometimes easier to work with. So again, for this linear stress-strain relationship, we can rewrite it in the variable coefficient form that's shown at the bottom. This is like the acoustics equations that we saw before. The only difference is that the matrix A now has k of x and rho of x in it, but that matrix is multiplying the derivatives of u and sigma. So it's the variation in k and rho is no longer inside the derivatives, it's outside. So we have qt plus a of x times qx equals 0. So it's a non-conservative system. But it's sometimes easier to think about the solution in terms of sigma, or the pressure in the case of linearization of gas dynamics, and the velocity. Those are sort of the natural quantities to think about, whereas strain and momentum are less natural. Also, as we'll see, when we look in terms of the stress or the pressure and the velocity, those variables turn out to be continuous at an interface, even if there's a discontinuity in the material properties as a wave passes through, whereas the strain and the momentum typically are not continuous. In fact, in the conservation form, what's required is that the fluxes be continuous at the interface, but the fluxes are exactly u and sigma. So the fluxes from the conservation form are the primary variables, the primitive variables in the non-conservative form, and those are the things that are continuous at an interface. And you can think of that in terms of the conservation laws. If you had a jump in the flux at an interface, then these x derivatives that appear in the conservative equations would be like delta functions at the interface, and we'd have some generation of mass or momentum at the interface, which shouldn't be happening. Yeah, so if we start with this system in the non-conservative form, qt plus a of x, qx equals 0, then in the case of a constant coefficient a, we saw that we could diagonalize the system by multiplying on the left by the inverse of the eigenvector matrix, where R of x is the eigenvector matrix corresponding to A of x. And we could linearize things by bringing in the R inverse AR, which is just the diagonal matrix L. And in the constant coefficient case, where R is not varying with x, then we could eliminate the R inverse of x from each side and write things in terms of the characteristic variables w. If we divide w to be R inverse times q, and we got a nice diagonal system of equations. The problem in the variable coefficient case now is that we end up with this slightly more complicated expression, and if we again let w be R inverse times q, the characteristic variables, then because of this variation in x, there's an additional term that comes in, which is the derivatives of the inverse of the matrix of eigenvectors. So R inverse of x, if that's actually varying with x, then its derivatives come into this term on the right-hand side, which acts as a coupling. So on the left-hand side, we have what looks like decoupled scalar advection equations for each component of w, but unfortunately they're coupled by the term on the right unless the eigenvectors are actually constant in space. So that means that a wave in one family can feed energy into the other families due to the source term. And in particular, if you have an interface between different materials, you typically see that if a nice simple wave in one wave family is hitting the interface, as it goes through the interface, it can generate a reflection in other wave families. And so things become more complicated. And if you have continuously varying density and bulk modulus, then you can be having essentially reflections going on constantly throughout your material. So we can't diagonalize in general. But we can still solve these problems with wave propagation type algorithms. And for this linear system that we're looking at for acoustics, we can calculate for each x what the eigenvalues and eigenvectors are. And of course, the matrix has the same form as what we had before. And so the eigenvalues are simply plus and minus c, but now where the sound speed c depends on x, but it's the square root of k over rho at each point x. And the eigenvectors have the same form as before. The one eigenvector has minus z in the first component, where z is the impedance, and the R2 eigenvector has plus z in the first component. So for each x, we can calculate the eigenvalues and eigenvectors. So to solve this numerically, we might use a finite value method where we assume that each grid cell has a different value of rho and k. And then at the interfaces between grid cells, we have jump discontinuities between these values. And using this eigenstructure, we can solve a generalized Riemann problem for what happens at such an interface. But before getting into a Riemann problem like that, let's just look at a couple of examples. So if we consider just a domain where we really have just one interface between two different materials, and we have constant properties in each, and so we have on the left side some density and bulk modulus rho L and KL, on the right side rho R and KR, then if the impedance ZL and ZR are equal, then it turns out that waves are transmitted through the interface without any generation of other waves. And that's because the eigenvectors, which are plus or minus z and 1 in the two components, those vectors would be the same in both materials. It's only when there's a jump in impedance between the two sides that you end up getting potentially reflections or change in the waves as they pass through this interface. And this is a problem that's been well studied for decades, and it's well known what that you can calculate transmission and reflection coefficients that tell us, for example, if we have a pressure pulse that's hitting an interface, then what fraction of that pressure gets transmitted and what is the pressure in the reflected wave. And for this case of acoustics, where we just have one left-going wave and one right-going wave. And notice that the reflection coefficient CR depends on the difference of impedances here. And so if the impedance is the same on both sides, then that's 0. And the transmission coefficient 2ZR divided by ZL plus ZR, again, if Z is the same on both sides, then that would simply be 1, and this would be 0 in this case if ZL equals ZR. But more generally, we'll have some transmitted wave and some reflected wave, and the reflected wave, notice, depends on ZR minus ZL, so whether it has a positive amplitude relative to the incoming wave or a negative one depends on which is larger, ZL or ZR. So let's look at an example first of the case where the two impedances are equal. So here's an example where ZL is equal to ZR. And so on the left we have Z is 1, and on the right Z is 1, and there's only a change in the sound speed. So this comes from choosing rho and k in such a way that rho times k is the same on both sides, but k divided by rho is different on the two sides. So what we expect in this case is that as the wave approaches the interface and goes through, there's no generation of a reflected wave, but there is a deformation in the transmitted wave because of the fact that the sound speed is smaller on the right than on the left. So it slows down as it goes through the interface, and as a result, it gets compressed. And of course, P and U are not conserved quantities in the system the way we've written it, since it's not in conservation form, but they do have this property that they remain continuous as we go through the interface. Look at that again. Here was the initial conditions, and as it goes through the interface, P and U both remain continuous, and the wave slows down, but the amplitude remains the same. The transmission coefficient is 1, and there's no reflected wave. The reflection coefficient is 0. By contrast, here's a case where the impedance is different on the two sides. Again, it's the same jump in the speed of sound from 1 to 1/2, but choosing material parameters so that Z goes from 1 to 2 as we go from one material to the other. And now we do expect that there'll be a transmitted wave, and the transmission coefficient is 4/3 in this case, and a reflected wave with coefficient 1/3. So that means the transmitted wave will actually have larger amplitude than the incident wave in pressure, and the reflected wave will also have a positive pressure that's 1/3 as tall as the incident pressure. And again, P and U remain continuous at the interface. So as the wave hits, we get both the transmitted and the reflected wave in this case. And the transmitted wave is higher than the original wave, but compressed again by the decrease in sound speed. The reflected wave is 1/3 the amplitude of the original wave. Okay, let's look at one more example, and this will lead us to looking at the Riemann problem, and also allow us to, once we understand the Riemann problem, understand how the transmission and reflection coefficients can be derived. So here I've taken a case where we just have a single wave. I've set the pressure and the velocity so that the incoming wave is just a single right-going wave. There's no left-going wave. So if we look in the xt plane, this is time going upwards here. In the xt plane, it's simply a wave moving to the right. And then when it hits the interface, because there's, again, the same jump as in impedance as the previous example, we'll have a transmitted wave that is going slower and has a different amplitude, and also a reflected wave in that case. So as it propagates along, we get the transmitted wave and the reflected wave, and in this simple case, each of those waves is just a simple jump discontinuity, now propagating with the appropriate speed in each medium. And if we go back a little bit to this time, I actually started the simulation here at time t equals -2, so that at time t equals 0 is the time when this wave has just hit the interface. And if we look at that time, then the data that we have here looks like a Riemann problem. It looks like a Riemann problem in which we have the left state over here and the right state over here. And in between, as we go forward in time now, we'll see one right-going wave in the right medium, a left-going wave in the left medium, and there'll be a single state Q sub m in between because of the fact that P and U are both continuous at the interface. So there's a single state in between those two waves. And so if we forget about time from -2 up to 0 and just look at this starting at time 0, we can consider this as a generalized Riemann problem where we have two different states, QL and QR, the jump in pressure and velocity, but we also have a jump in the material parameters that we have in the material on the left. We have one set of material parameters, on the right a different set. But what we see when we solve that Riemann problem is that we have one wave that's moving to the left, which is simply moving through the material on the left, and we know how to find a wave that's moving through that material. That's just a constant material it's moving through. We can calculate the R1 eigenvector for that material. And similarly, the transmitted wave is that in the context of a Riemann solution is the right-going wave that comes out of the Riemann data, and it's simply propagating into the material on the right. So the jump across that wave must be proportional to an eigenvector based on the coefficients in the right state. So that allows us to work out what the solution of the Riemann problem is for this sort of situation. So the Riemann problem for the heterogeneous medium will assume that k of x and rho of x, our material parameters, are piecewise constant, and that they have a jump in their values at x equals 0, the same place where we have a jump in q in our Riemann data. And then to solve the Riemann problem, we can think of it as simply taking that jump in q and writing it as a linear combination of two eigenvectors as usual. But now the left eigenvector corresponds to the left-going wave, and so for the left-going wave, we would want to use the eigenvectors in the material that's on the left, and so we want to use the value of KL and rho L, the material parameters on the left, whereas the right-going wave we would use the eigenvector for the material on the right. In this case, for acoustics, there's only one eigenvector going in each direction, but if you look at a more complicated system of equations, you could have more than one wave going in each direction, but the idea would be the same. If we have a piecewise constant material, then to the right we have one set of eigenvectors, the right-going eigenvectors. To the left we have the left-going eigenvectors, and they may depend on different material parameters. So for the case of acoustics, where the eigenvectors are minus E1 and plus E1, we can easily work out the inverse matrix. And so the idea now to solve this generalized Riemann problem is that whatever jump in Q we have, the jump in pressure and the jump in velocity, we want to write it as a linear combination of minus ZL1, which is the eigenvector corresponding to the left-going wave in the material on the left, and ZR1, which is the eigenvector corresponding to the right-going wave through the material on the right. And so if we can find these coefficients alpha 1 and alpha 2, then that tells us what the two waves W1 and W2 are, and then they propagate at speeds that are given by the speed of sound in the two materials. So the left-going wave is propagating with speed minus CL in the left state. The right-going wave is propagating with speed plus CR in the right state. And to calculate alpha 1 and alpha 2, since we know QR minus QL, this is just a linear system of two equations for alpha 1 and alpha 2. And here's the picture again in the xt plane. So when we have this discontinuity in the initial values, we have different states, ZL and ZR over here, and different wave speeds, CL and CR, on the two sides that give the wave speeds of the two waves. And then we have data QL and QR, and everywhere in between we'll have QM. And again, we're using the fact that we know the solution should be continuous across the interface to say that there's a single state QM, and so the only discontinuities in this Riemann solution are the two here, one that's proportional to the eigenvector R1 on the left and another wave that's proportional to the eigenvector R2 on the right. And so if we define a matrix R LR by taking the eigenvector for the left-going wave in the left and the eigenvector for the right-going wave in the right and make those the columns of the matrix, then we just have this linear system to solve for the alpha 1 and alpha 2. That matrix times QR times alpha is equal to the jump in pressure and velocity, QR minus QL. And we can easily work out what the inverse is of that matrix, and that gives us this expression for alpha 1 and alpha 2. And so if we look at the particular case of the simulation I showed where we just have an incident wave that is some multiple of the R2 vector in the left material. So that means if this is our interface, that means we're looking at a wave that's simply moving from to the right in the left material, and it was starting at some point over here. And then it's hitting this interface, then if we look at that particular case, then the Riemann problem that's sort of defined at the time when it hits the interface has a jump in Q that's simply proportional to the R2 eigenvector in the left state. And then we can figure out what happens when we solve that Riemann problem, and we'll find that we get a left-going wave, which is proportional to the left-going wave in the left state, but also a right-going transmitted wave that's proportional to the right-going wave in the right state. And if we use the formulas on the previous slide, that means the alphas are just that R inverse matrix times the jump in Q. And for this particular initial data up here, we end up with this expression for alpha 1 and alpha 2. And so we get alpha 1 and alpha 2 are values that look very much like these reflection and transmission coefficients, although notice that in alpha 2, this is 2ZL on top rather than 2ZR. But when you look at how does the pressure change as you go through the interface, it turns out that the pressure jump in the transmitted wave turns out to be exactly the transmission coefficient times beta times the pressure jump in the initial wave, which was beta times ZL. And the pressure jump in the reflected wave turns out to be the reflection coefficient times beta times ZL. So the pressure jump in the incident wave is beta ZL, and that gets split up into transmitted and reflected parts. And then, of course, the second component in each vector is the appropriate thing so that you have a purely left-going and right-going wave for each of these. So how would we use this in a finite volume method? Well, we would think of taking our initial data and, as usual, viewing it as piecewise constant if we just want to use Godunov's method. But in addition to taking piecewise constant initial data Q, we would also take piecewise constant material parameters, rho and K. And so then when we have a Riemann problem in each time step, at each of these Riemann problems, we have exactly the sort of problem we were just looking at. So at this Riemann problem, we would end up getting a left-going wave that's appropriate to the material parameters in that state, but a right-going wave that's appropriate to the material parameters in that state. And notice that the left-going wave at the next interface will have the same speed of sound as this one, so those two velocities will be opposites of each other. Similarly, these two velocities are negatives of each other. But we can solve the general Riemann problem that arises at each cell interface and compute the waves from that. And then you can use all of the machinery of the wave propagation algorithm to extend this to second order methods and apply limiters to these waves exactly the same way you do for a nonlinear problem, and come up with a method that works quite well for wave propagation in heterogeneous media. So I'm not going to go through the details of any of that. It's basically the same as what we do in a nonlinear problem, for example, the way the limiting is done. Because the eigenvectors are changing from each cell interface to the neighboring interface, you have to also look at the projection of one wave on its neighbor in order to apply limiters, but it's the same thing as in the nonlinear case. So now let's turn to two-space dimensions for the two-dimensional acoustics equations with variable coefficients have exactly the same form as the constant coefficient case, but now again rho and k can be functions of x and y in two-space dimensions. And so we can define a Riemann problem in the x or y direction at each cell interface. And for example, in the x direction, we have eigenvectors. We now have three eigenvectors that, again, the W or R1 and R3 just look like the eigenvectors for acoustics in 1D with a 0 in the third component. And the new eigenvector that comes in has a jump in the v velocity, but no jump in p or u. And again, we're now going to assume that we've averaged these material parameters onto grid cells so that in each grid cell we have average values of the impedance E in particular. So the right-going wave is going to involve Zij in the ij cell, whereas the left-going wave would involve Zi-1j, assuming we're at the interface between cells I-1j and ij here. But we can solve the Riemann problem for arbitrary jumps in p, u, and v with this set of eigenvectors. We form a matrix that has three columns given by these three eigenvectors, and then we can solve for what the alpha 1, alpha 2, and alpha 3 are that come out of that. And the wave speeds, again, the left-going wave, S1, would be speed minus Ci-1j, based on the sound speed in the cell to the left, whereas the 3 wave is moving into the cell on the right, so it has speed plus Cij. And the wave in between has speed 0, since we've linearized about 0 velocity. And so when we apply the wave propagation algorithm and limiters and whatnot, we really only have to work with waves 1 and 3. Wave 2 doesn't add anything because we always multiply the waves by the speeds and in terms of the fluctuations and the updates that are made. So this is a case where even though we have a system of 3 equations in the Riemann solvers, we really only have to work with 2 waves. And as we saw in the lecture on two-dimensional wave propagation algorithms, if we're using ClawPack, for example, then we need a Riemann solver that solves this Riemann problem and splits things up into waves, and that's exactly what we've just been looking at. And if you want to use dimensional splitting, that's all you need. If you want to use the full unsplit method, then we also need a transverse Riemann solver that splits the right-going and left-going fluctuations into parts that are sort of upgoing and downgoing. And we can do all of this in the variable coefficient case. It's just that now our splitting is going to depend on the material parameters to the left and the right for the normal splitting. And in 2D, that normal Riemann solve is again exactly like the 1D Riemann solve in the x direction. And in the y direction, it's very similar, only it's the pressure and velocity that determine the waves, and the u variable just has a stationary discontinuity. But the transverse Riemann solver gets a little more interesting in the variable coefficient case. If you remember, in 2D, if we have these fluctuations going to the right and the left, then the idea is that the right-going fluctuation, for example, we should really split up into part that's also going upwards and part that's going downwards. And the left-going fluctuation should also be split up into an upgoing part and a downgoing part. And in the case of constant coefficient acoustics, it would be natural to take, say, the right-going fluctuation, a plus delta q, and simply split that into the eigenvectors of B, where B is the acoustics matrix in the y direction. And in the constant coefficient case, we could use that same B matrix to calculate the upgoing part and the downgoing part. But in the variable coefficient case, those eigenvectors of B are going to be different in the cell above than they are in the cell below. And both of those are potentially different from the cell that we started out in. So how do we do the splitting into these transverse waves for variable coefficient acoustics? Which one of those sets of eigenvectors do we use? Well, it turns out that the best thing to do typically is to also take into account the fact that a wave that's going to the right, if it starts to go upwards into the cell above, for example, only part of it may go into that cell and part of it may be reflected. We should really look at the reflection and transmission of a wave as it's moving upwards and to the right, for example. So as we look at this wave coming up here, we should take the right going part, but then rather than just splitting it up into either set of eigenvectors of B for the cell up above or the cell down below here, we should look at how a wave that's moving in this direction that strikes this interface gets split up into a transmitted part and a reflected part, and apply that splitting to the right-going wave or the right-going fluctuations, or the combination of right-going waves, in order to determine the part of that that should really affect the cell up above. So if we look at solving the Riemann problem first in the x direction, then we have these left-going and right-going fluctuations. And now if we want to, for example, look at the B minus A plus fluctuation, that's the downward going part of the rightward going fluctuation A plus, then we should look at what part of that is transmitted at the interface and what part of it is reflected. And so we can look at taking this jump in this fluctuation, that's a vector with 3 components for acoustics. We can look at taking that vector and split it up as a linear combination of 3 eigenvectors in the y direction. But for the downgoing eigenvector, we'll use the value of z in the cell down below, whereas for the upgoing eigenvector, we'll use the value of z in cell ij. And the speed, similarly, the downgoing wave will have speed given by the speed of sound in the cell below, whereas the upgoing portion will have the speed of sound in the cell that we're in. So this is, again, where we're looking at an interface, the right-going part, and now we're trying to calculate what part of that is downgoing. And so we're using these 2 cells to determine that. For the upgoing part, we'll see we have to use 2 different sets of eigenvectors, but for the downgoing part, those are the 2 ones to use. And we only really need the downward going part since we're just trying to figure out how does this affect the flux at the interface down below. So again, if we're looking at the part that's going to the right and downwards now, that's the part, this little triangular part here is what's affecting the flux, the G flux, G tilde flux at this interface down below. And for that, we only need to calculate the part that's downgoing, which is really just this component here. The upgoing part we're not going to worry about for the moment. We'll look at that later. And so B minus A plus delta Q is simply the wave speed, which is the negative of the sound speed in the cell down below, times the wave, which is the component of the splitting of A plus delta Q into eigenvectors based on the 2 cells that we're looking at. And so that's how we would define B minus A plus delta Q. Now, if we want to look at the upgoing part of that A plus delta Q, then we have to do something similar, but now we want to look at the eigendecomposition where we use the downgoing eigenvector in the cell ij, but the upgoing eigenvector in the cell up above, ij plus 1, and that wave is propagating with speed cj plus 1, and then it's only that wave that comes into the update there, so we only need that upward going wave, the beta 3, and B plus A plus delta Q is the wave speed times that wave. So it's a fairly minor modification of what we would do for constant coefficient acoustics, but we need to keep track of the material parameters in each cell and work out these eigendecompositions based on those varying coefficients now. Oh, another thing to mention briefly is that if we have some rho and k that are varying in space, but now we're solving the problem on a grid, then we need these cell averages of some sort rho ij, kij, zij, and cij that are used in the formulas we just used. And so a natural way to average a varying coefficient is to simply take the integral over the cell and divide by the size of the cell. And it turns out that's the right thing to do for the density, but for the bulk modulus, it turns out that instead you have to use what's called the harmonic average, where we take 1 over k and then average that over the cell and then invert that result. This combination of rho and k for the cell gives a better approximation to how waves are actually propagating in a heterogeneous material. And there's a bit of discussion in that in section 914 in the book, if you want to see sort of a justification of that. And in particular, if we're looking at, say, a Cartesian grid, and we have just a sharp interface between different material properties, and we have one set of properties on one side and another set on the other side, then over a grid cell, we would, for example, take the fraction of the cell that lies in the left state and compute the fraction of the cell that lies in the right state, and then we could average the density. If it was piecewise constant density across that interface, we could compute an average density by simply weighting the rho on the two sides by the corresponding averages, by the corresponding areas. But in order to calculate the proper kij, we would want to take that weighted average of 1 over k and then invert the result in order to get the kij in the grid cell. And once you've averaged rho and k appropriately, then you can compute the sound speed and the impedance in the cell from the usual formulas. So here's an example of that sort. That's figure 21.2, I think, in the book. Actually, this is figure 21.1 that shows the discontinuity, but then there's some computation shown that we'll look at in a moment. So this is a case where we have a left and right state with different material parameters shown on the right here, and we can calculate the transmission coefficient is 2/3 and the reflection coefficient is -1/3 in this case. In this case, the ZR is less than ZL. So we end up with a negative value for the reflection coefficient, and the pressure gets sort of negated in the reflected wave. And I've chosen an interface here between the left and right states that isn't aligned with our Cartesian grid. Again, we're using a Cartesian grid here, so we will have to average the values within each grid cell based on the fraction of the cell that's on either side and using the appropriate mean value and harmonic average for rho and k respectively. But if we do that, then we can now look at what happens if we take a wave that's hitting this interface. So in this particular example, the initial data is a pulse in pressure, just a square wave in pressure, and a velocity that's chosen so that it gives a purely right-going wave initially. And then as it hits this interface, it gets partly reflected and partly transmitted. And of course, it's a little more interesting down in here, where the wave, sort of the transmitted wave from here and the transmitted wave from this edge of the wedge here, which comes in at some angle to the grid, are interacting with each other, and the reflected wave out here. And by the colors here, you can see that the pressure in the reflected wave is negative, whereas the pressure pulse that came in originally was positive, a reflection of that negative value for the reflection coefficient. Another thing you could do with this example is to choose material parameters in this area down here in this wedge that sort of correspond to a much more rigid elastic body than what's out here, so that the waves are nearly entirely reflected, so that this is acting more like a solid wall boundary. And that would be one way to sort of simulate wave propagation in a region that's not rectangular, but still solve it on a rectangular grid with effectively a solid wall boundary condition. So here I've chosen the same values on the left as before, but on the right, the density is 10 to the 4th, and the bulk modulus is 10 to the minus 8th, so that we end up with an impedance that's 0.01. So we have a big impedance jump here from 1 to 0.01, and the sound speed on the right also turns out to be very small, 10 to the minus 6, which is good because it doesn't restrict our time steps. Our method is going to be stable if we choose our time step based on the sound speed on the left. And in this case, the transmission coefficient is only 0.02, and the reflection coefficient is minus 0.98. So we have almost complete reflection at this interface, and it's really behaving more like a solid wall. You could even ramp up these values to larger values if you wanted to have it even more like a solid wall. And so here it's the same experiment as before, but with this case, and you can see that as it propagates, we're getting almost all of the energy is reflected in this case, and very little is transmitted into this other region. If you zoom in on the plot of U, then you can see that there are in fact some sort of artifacts right around the boundary, but for the most part it looks pretty clean. Of course, if you were really trying to solve this problem with a solid wall here, it would probably be better to use a grid that's more conforming to the boundary and then impose a solid wall boundary condition. But a big advantage of this approach is that you can handle much more complicated geometries without having to deal with boundary conditions, and you can handle intermediate states where you don't have a purely solid reflecting material, but something that's more intermediate. So as one final example, just to show that you can handle more general geometry here, this is an acoustic wave hitting a set of circular inclusions. So this is going back to the material parameters from the first example where there's not such a great impedance jump, but there is some impedance jump, and so you get some reflection at these interfaces. And I've taken this somewhat narrower pulse here so that we can see those a little bit better. And so as it hits this circular inclusion, you can see that we're getting, of course, the reflected wave out here, but also the transmitted wave inside is moving slower. I had the slower sound speed inside than outside, and so you can see that effect. And then as it starts to hit these other inclusions, we get more reflected waves from those, and much more interesting interactions at later time. So with this approach, it's possible to handle quite arbitrary geometry even on a Cartesian grid like this. And of course, with the addition of adaptive mesh refinement, you can really zoom in to look at even much narrower pulses of pressure or high frequency wave oscillations to some extent. If you have very high frequency oscillations and hundreds or thousands of wavelengths within your domain, then these effectively second order accurate methods wouldn't really be appropriate. You would have to resort to something higher order. But for many problems, you can get a fairly nice solution with these approaches.